Welcome to this comprehensive guide on applications of integration. In calculus, integration is a powerful tool that allows us to solve complex problems by breaking them down into infinitesimal pieces and adding them up. Today, we'll explore 7 key applications of definite integrals. First, finding displacement from velocity. Second, calculating areas between curves. Third, computing volumes using the disk and washer methods. Fourth, finding volumes using the cylindrical shell method. Fifth, determining the arc length of curves. Sixth, calculating surface areas of revolution. And seventh, exploring physical applications like work and fluid pressure. Let's begin our journey through these fascinating applications of integration. Let's start with our first application, velocity and net change. When we have the velocity function v of t of an object, the definite integral of this function gives us the displacement, or net change in position, over a time interval. Mathematically, if v of t is the velocity at time t, then the displacement over the interval from a to b is given by the definite integral from a to b of v of t dt. If we want the total distance traveled, which is always positive regardless of direction, we integrate the absolute value of the velocity or the speed. Let's work through an example. Suppose an object moves with velocity v of t equals 3t squared meters per second for t from 0 to 2 seconds. To find the displacement, we compute the integral from 0 to 2 of 3t squared dt. This equals the antiderivative, t cubed, evaluated from 0 to 2. That gives us 2 cubed minus 0, which equals 8 meters. Now, let's move on to our second application, finding the area between curves. When we have two continuous functions f of x and g of x on an interval from a to b, the area of the region between these curves is given by the integral of their difference. Mathematically, if f of x is the upper curve and g of x is the lower curve, then the area between them from a to b is the integral from a to b of f of x minus g of x dx. Let's consider an example. Find the area between y equals x squared and y equals x from x equals 0 to x equals 1. First, we need to determine which function is higher in our interval. Since x is greater than or equal to x squared when x is between 0 and 1, x is our upper function, and x squared is our lower function. So, we compute the integral from 0 to 1 of x minus x squared dx. This equals the antiderivative, 1/2 x squared minus 1/3 x cubed, evaluated from 0 to 1. That gives us 1/2 minus 1/3, which equals 1/6 square units. Our third application is finding volumes by slicing, specifically using the disk and washer methods. When we rotate a region about an axis, we create a three-dimensional solid. The disk method is used when there's no hole in the resulting solid. For a region bounded by y equals f of x, the x-axis, and the vertical lines x equals a and x equals b, when rotated about the x-axis, the volume is given by the integral from a to b of pi times the radius squared dx. Here, the radius is f of x. The washer method is used when the rotated region has a hole. If we have an outer radius r of x and an inner radius r of x, the volume is given by the integral from a to b of pi times the difference of the squares of the outer and inner radii dx. Let's look at an example of the disk method. Rotate the region bounded by y equals the square root of x, the x-axis, and the vertical line x equals 4 about the x-axis. Here's our region. When we rotate it around the x-axis, we get a solid where each cross-section is a disk with radius equal to the square root of x. The volume is the integral from 0 to 4 of pi times the radius squared dx. That's pi times the integral from 0 to 4 of x dx, which equals pi times 1/2 x squared evaluated from 0 to 4, resulting in pi times 8, or 8 pi cubic units. Our fourth application is finding volumes using the cylindrical shell method. When we rotate a region about a vertical line, like the y-axis, it can sometimes be easier to use the cylindrical shell method rather than the disk or washer method. For a region bounded by y equals f of x, the x-axis, and the vertical lines x equals a and x equals b, when rotated about the y-axis, the volume is given by the integral from a to b of 2 pi times f of x dx. Here, x represents the radius of each shell and f of x is its height. Let me explain the concept of a cylindrical shell. Imagine taking a thin vertical strip from our region at a distance x from the y-axis. When we rotate this strip around the y-axis, it forms a cylindrical shell with radius x and height f of x. Let's work through an example. Find the volume of the solid formed by rotating the region under y equals x from x equals 0 to x equals 1 about the y-axis. Using the shell method, the volume is the integral from 0 to 1 of 2 pi times x times the height x dx. That's 2 pi times the integral from 0 to 1 of x squared dx, which equals 2 pi times 1/3 x cubed evaluated from 0 to 1, resulting in 2 pi divided by 3 cubic units. Our fifth application is finding the arc length of a curve. The length of a smooth curve, y equals f of x from x equals a to x equals b, can be calculated using integration. The formula for arc length is the integral from a to b of the square root of 1 plus the square of the derivative of f of x with respect to x dx. This comes from using the Pythagorean theorem on infinitesimal segments of the curve. Let's consider an example. Find the length of the curve y equals x cubed divided by 3 from x equals 0 to x equals 1. First, we compute the derivative, f prime of x equals x squared. Then, we substitute into our arc length formula. The length equals the integral from 0 to 1 of the square root of 1 plus x to the 4th power dx. This particular integral doesn't have an elementary antiderivative, but it can be approximated numerically or expressed in terms of special functions. Our sixth application is calculating the surface area of a solid of revolution. When we rotate a curve y equals f of x around the x-axis, we generate a surface. The area of this surface can be found using integration. The formula for the surface area is 2 pi times the integral from a to b of f of x times the square root of 1 plus the square of the derivative of f of x dx. Here, f of x represents the radius at each point, and the square root term accounts for the arc length element. Let's look at an example. Find the surface area when the curve y equals square root of x from x equals 0 to x equals 1 is rotated about the x-axis. First, we find the derivative. F prime of x equals 1 divided by 2 times the square root of x. Substituting into our formula, we get the surface area equals 2 pi times the integral from 0 to 1 of square root of x times the square root of 1 plus 1 divided by 4x dx. This simplifies to 2 pi times the integral from 0 to 1 of square root of x plus 1/4 dx. This integral can be evaluated with an appropriate substitution, and the result is approximately 4.68 square units. Our final application covers physical applications of integration, such as work and fluid pressure. In physics, work is the product of force and displacement. When the force varies, we use integration to find the total work done. For example, to find the work required to lift an object with varying mass distribution, we integrate the product of the gravitational force and the height. Work equals the integral of y times g times rho times a of y dy, where rho is the density and a of y is the cross-sectional area at height y. Another application is calculating the total force due to fluid pressure on a submerged surface. Pressure at depth y is given by P of y equals rho times g times y. The force on a small strip of width w at depth y is dF equals P of y times w dysprosium. The total force is found by integrating. F equals the integral of rho times g times y times the width at depth y, dysprosium. Let's consider an example. Find the force exerted by water on a triangular plate submerged vertically in water, with its top vertex at the water surface and its base of 4 meters parallel to the water surface at a depth of 3 meters. The width of the plate at depth y is proportional to y, specifically w equals 4y divided by 3. The force is the integral from 0 to 3 of rho times g times y times 4, y divided by 3 dysprosium. That's 4 rho g divided by 3 times the integral from 0 to 3 of y squared dysprosium. This equals 4 rho g divided by 3 times y cubed over 3 evaluated from 0 to 3, which gives us 4 rho g times 9 divided by 9, or 4 rho g newtons. With rho equals 1,000 kilograms per cubic meter and g equals 9.8 meters per second squared, the force is 39,200 newtons. We've now explored 7 key applications of integration: velocity and net change, area between curves, volume by slicing, volume by cylindrical shells, arc length of curves, surface area of revolution, and physical applications. The power of integration lies in its ability to add up infinitely many infinitesimal quantities to find total values of various measures. Whether calculating a displacement from velocity, area from a height function, or force from a pressure distribution, the The definite integral provides a systematic way to compute these quantities. Remember that many of these applications follow a similar pattern. Identify the infinitesimal contribution, express it as a function, and then integrate over the appropriate interval. With these techniques in your mathematical toolkit, you'll be able to solve a wide range of problems in calculus, physics, engineering, and beyond. Thank you for watching this comprehensive guide to applications of integration.